So we'll start off with the principal component analysis. So it's basically about uh, exploratory technique for multivariate data. Right? So principal component analysis tries to explain the variance covariance structure of a set of variables through a few linear combinations of these variables. So you're basically trying to create a new dimension, which is a linear combination of existing variables. Its general objective is data reduction or dimension reduction, right? So it's also called as a dimension reduction technique, and obviously interpretation. Principal component analysis is often more effective in summarizing the variability in a set of variables when these variables are highly correlated. So if two variables are highly correlated, that is where you try to use them. It's also a very good means of reducing the problem of multicollinearity. So if two variables are very highly correlated, when you're doing some other technique like say linear regression, you might transform them into a new dimension by using principal component analysis, wherein the sum total effect of their variability is captured and the existing two variables are removed from the whole data analysis. It's also a technique for transforming a set of observed variables into a new set of variables that are uncorrelated with each other. That is what is about understanding multicollinearity and reducing it by using principal component analysis. The first principal component is the weighted combination of the k observed variables that account for the most variance in the original set of variables. So when you're expecting that there are two variables which are highly correlated and they're talking about a y, your principal component analysis tries to tilt this weight on one of the dimensions so that the other shows least amount of variance and one shows the highest amount of variance. That is the intention of principal component analysis. So as you can see from the equation, PC1, that is first principal component analysis, or the first principal component, is equal to a1 x1 plus a2 x2 plus ak xk and so on. So here in the eigenvalues and the eigenvectors, so these are usually done by orthogonal transformation and that of the axis, and that is why the eigenvalues, that is the distance measurement, becomes an important factor, and the vector is also the most important aspect. Now somewhere we need to understand vector computations over here. The difference between normal statistical means and vector computations is that a vector has a direction as well as a magnitude, and you can shift anything, a point or a line, from one dimension to the other dimension, so as long as we maintain the magnitude and the direction. So if something was there in the first quadrant of the four axis, so you see there are four quadrants, right? So one is plus plus, one is plus minus, one is minus plus, and one is minus minus. So if you want, you can move them across this as long as the direction remains the same and the magnitude of the vector remains the same. It's applicable. So that is utilized more often in something like support vector machines, right? So this is one of the very initial steps of stepping into vector computations. Now an eigenvalue of greater than 1 indicates that the principal component accounts for more variance than accounted by the original variable in standardized data, and this is commonly called as a cutoff point for which principal components are retained. Eigenvalues provides the weights to compute the uncorrelated principal components, which are the linear combination of the centered, standardized, or centered, unstandardized original variables. So one thing is very clear, it's a transformation from multiple dimensions to a few dimensions. So it's a variable reduction technique in a way. So the principalcom function produces an unrotated principal component analysis. I told about orthogonal transformations. So this one doesn't do that. So there is something else which we'll be doing later for that. So the principal component analysis, which is achieved by PRINCOMP function, does this of producing a principal component without the rotation, right? So there is rotation and without rotation. So you can see the structure is like you can just call the printcom function, pass the data, you say core is equal to true, use core is equal to false to base the principal components on the covariance matrix, right? If you want to base it on the covariance matrix, then you have to say correlation is equal to false, right? And then you do a summary of this object, and then you can check for the loadings as to how the loadings are. You can plot it using a scree plot also, you can do a biplot also, right? So we'll be doing all of this. Now the principal component function in the psych package can be used to extract and rotate the principal components. So the princomp, that functionality doesn't give you the rotation aspect, whereas the principal function, which is present as part of the psych package, allows you to do the transformation in terms of rotation of the axis also, right? So there is a varimax aspect also, so you can retain 5 components. So you just have to load the package. You have to call the principal function, in which you will first parse the data, the number of factors which you expect, you can pass it over there. You can say rotate, and in that rotate you can specify the functionality, whether you want varimax and min function, whatever you want. Rotate can be none also, it can be quantimax, promax, oblimin, simply max, or cluster, whichever you prefer based on your requirement. This all flows from the domain in which you're trying to use, right? Look at the application of the principal component analysis by way of very simple examples. Obviously you can use these exhaustively, and the depth is far humongous than what we are going to see on the screen. So first of all, let's just get the data again. So I'm saying data USRS, right? So I'm just loading this again. I'm allocating that data to an object called USA. Okay, right? So I got the data, and then I'm saying fit 9. You can use any object name of your choice. I'm saying print comp. Right, this is the very basic one, which doesn't allow you the rotation aspect. You pass the data over here, and correlations COR is equal to true. That means you are not going to use the covariance matrix, right? So you're using the correlation matrix, and press enter. So you get the fit, right? You can also do a fit 10 allocation sign, same print comp USA data, and in this case you can say COR is equal to false, where you're using the covariance matrix. So fit 9 and fit 10, right? And you can do a summary of fit 9, right? And similarly you can, if you want, the summary of 10 also. Right. So you can look at the components. Now these are different because you have used in one case the correlation, in one case you have used the covariance, and obviously these will be different. So you have created 4 components. So one is the base, right? So you have the standard deviations for the component. So the deviations will reduce as you're going away. So this is the first component. It is having the highest weight, right? The proportion of variance is very high in this case, and it will go on reducing as you move towards the 4th component. And the proportion, the cumulative proportion, you can see is 0.62, because when you look at the whole component spectrum, all of this add to 1. So these together make a dimension, right? Okay. So now what you can do is you can do a loadings of fit 9. So there is a function called as loadings of fit 9. So it will show you that, okay, within this components, what is the weightage of each of these components. So that's how it is structured, right? This is the sum of squares loadings for component 1, proportion, cumulative variances, because this adds up to total 1. So 25 plus 25 is 50, 50 plus 25 is 75, 75 plus 25 is 1 over here. In the 4th component, this variable is not considered. Okay, you can do a plot of the same. So you can say plot fit 9. You can do a plot over here. You can see the plot, and you can see that the variance is highest for first component, and it is reducing as you go for the last component. If you want, you can also do a fit $9 scores, right? So it will show you for all the observations, and that becomes a little bit tacky for us, but yes, it's available if you want to indulge into that also. And then you can do a biplot of fit 9. zoom it. So that's how the new dimension is created. You can see these are the components, the 4 components which you have created, right? That's how you can see it. So, and these are the dimensions: component 1, 2, 3, 4. On the 4 dimensions you have created a new virtual world in itself, right? That's where you are trying to increase the variance on one and reduce the variance on the others, right? So you can see that on the screens also, right? This is the same output which we have already seen. So the loading explains the correlation between the components and the original variables. So higher the loading, that means it's explaining more about the original variables. Lower the component, it means lower the loading, that means it's explaining less. So you can term loading as a weightage. The combination of positive and the negative loadings are interpreted as mixed, right? And we had seen this funnel plot also. So we know that the variance is highest for the first component and least for the fourth component. And this is the biplot, which displays in a typical visualization technique for understanding the interrelationship between the observations and the variables in the multivariate data.